Hello, science fans. Welcome to the amazing world of machine learning, or as I like to call it, teaching computers to think. Imagine you have a new puppy. You teach it to sit by saying sit and giving it a treat when it does. At first, it's just guessing, but soon it learns the pattern. Machine learning is a lot like that, but instead of puppies, we're teaching computers. And instead of treats, we use data. Lots and lots of data. It's how we help machines learn from experience without us having to write rules for every single possibility. It's not magic, it's science. So why do we do this? Well, think about all the information in the world. It's a huge, messy pile of pictures, numbers, and words. No human could ever sort through it all. But a computer, once it's trained, can do it incredibly fast. It can find patterns we might miss, make predictions about the future, and help us solve some of the world's biggest problems. From helping doctors spot diseases earlier to making your phone's camera smarter, machine learning is a powerful tool that is changing our world in countless ways every single day. Consider this. The core idea is beautifully simple. We give a computer a goal and a ton of examples. For instance, we show it thousands of pictures of cats and dogs, telling it which is which. Over time, the computer builds its own internal rules or a model for telling them apart. It learns to look for pointy ears, whiskers, and certain snout shapes. This model can then look at a brand new picture it has never seen before and make a very educated guess. This process of learning from data is what makes machine learning so incredibly useful and versatile. This ability to learn and adapt is what separates machine learning from regular computer programs. A normal program follows instructions we give it, step by step, and that's all it can do. But a machine learning model can improve on its own as it gets more data. It's like the difference between a cookbook with a fixed recipe and a chef who tastes the soup and decides it needs a little more salt. The chef learns and adjusts. That's what we're doing here. We're training digital chefs to help us make sense of the universe. So let's get our aprons on and dive in. First up is a task called classification. This is just a sciencey way of saying sorting things into piles. Is this email spam or not spam? Is that a picture of a car or a bicycle? Is a medical scan showing a healthy cell or a diseased one? These are all classification problems. We're asking the computer to look at something new and assign it a label from a set of choices. Models like logistic regression, decision trees, and powerful neural networks are fantastic at this. They learn the key features that separate one group from another, becoming expert sorters for almost any kind of data you can imagine. Next, we have regression. This sounds complicated, but it's all about predicting a number. Instead of asking which category, we're asking how much or how many. For example, how much will a house sell for next year? What will the temperature be tomorrow afternoon? How many people will visit a website next month? These are regression problems. Models like linear regression draw a straight line through the data to find the trend, while more complex models like tree-based systems can capture more wobbly, complicated relationships. It's like being a digital fortune teller, but one that uses data and math instead of a crystal ball. Then there's the fascinating world of clustering. This is what we use when we don't have labels for our data. We just have a big jumble of information, and we want the computer to find natural groups or clusters within it. Imagine you have a box full of mixed-up socks. Clustering is like a machine that automatically pairs them up based on their color, size, and pattern, without you telling it what a pair is. Models like K-means and DBusCan are brilliant at this. They can help businesses find different groups of customers or help biologists discover new categories of plants based on their genetic makeup. These three tasks, classification, regression, and clustering, are the fundamental building blocks of so much of machine learning. They represent the most common questions we want to answer with data. Are we sorting things into known buckets? Are we predicting a future value? Or are we trying to discover hidden structures we didn't know existed? By understanding this core trio, you've already grasped a huge part of what machine learning is all about. It's all about asking the right question to solve the right problem. It's a powerful way of thinking. Now let's get into some really cool stuff, starting with computer vision. This is how we teach computers to see and understand the world through images and videos, just like we do. How does your phone unlock just by looking at your face? How does a self-driving car see pedestrians and stop signs? The answer is often a special kind of model called a convolutional neural network, or CNN. A CNN is inspired by our own visual cortex. It learns to recognize simple shapes first, like lines and curves, and then combines them to identify more complex objects like eyes, wheels, and eventually, entire faces and cars. Next, we have natural language processing, or NLP. This is all about teaching computers to understand and use human language. Every time you talk to a voice assistant, use a translation app, or see your email finish your sentences for you, that's NLP at work. Models like recurrent neural networks, or RNNs, and the incredibly powerful transformers are the stars here. They are designed to understand the order and context of words, which is super important in language. Dog bites man means something very different from man bites dog, and these models get that. They are bridging the gap between human communication and computer logic. Sometimes our data is just too big and complicated. It might have hundreds or even thousands of features, making it hard to work with. This is where dimensionality reduction comes in. It's a way of simplifying data without losing the most important information. Think of it like taking a big, detailed three-dimensional model of a car and creating a simple two-dimensional blueprint of it. The blueprint is much simpler, but it still shows you the car's essential shape and parts. Techniques like PCA and TSNE help us do this, making our data easier to visualize and our other models run faster and more efficiently. These advanced areas are where machine learning truly starts to feel like science fiction becoming science fact. From machines that can see and interpret the world around them to computers that can hold a conversation, these models are pushing the boundaries of what is possible. They handle incredibly complex, messy, and sequential data, the kind of data that describes our world. By learning how images are constructed, how sentences are formed, and how to find the simple truth in complex datasets, these models are giving us brand new superpowers to understand our universe. Finally, let's talk about one of the most exciting frontiers, reinforcement learning. This is all about teaching a machine to learn by trial and error, just like a person learns to ride a bike. The computer, or agent, takes actions in an environment to try and achieve a goal. When it does something that gets it closer to the goal, it gets a reward. When it makes a mistake, it gets a penalty. Over millions of trials, it learns a strategy or policy that maximizes its rewards. This is how computers have learned to master complex games like chess and Go, and it's how we're teaching robots to perform delicate tasks or manage city traffic flow. All these different models and techniques form a powerful toolkit. The key is knowing which tool to use for which job. If you want to sort things, you use classification. If you want to predict a number, you use regression. If you want to find hidden groups, you use clustering. If you're working with images, you reach for a CNN. And if you're working with language, you'll likely use a transformer. Each model is a specialist, designed to excel at a particular kind of problem. Understanding the problem is the first and most important step. So what have we learned? We've seen that machine learning is about teaching computers to learn from data. We explored how classification sorts things, regression predicts numbers, and clustering finds groups. We saw how advanced models can understand images with computer vision, process language with NLP, and simplify data with dimensionality reduction. And we peeked into the future with reinforcement learning, where machines learn through experience. It's a vast and incredible field, but it's built on these core, understandable ideas. Every complex system is built from simple parts. Don't be intimidated by the fancy names or the complex math behind them. At its heart, machine learning is about curiosity, experimentation, and finding patterns. It's a tool that anyone can learn to use to explore data and solve problems. So go ahead, be curious. Ask questions, look at the world around you, and think about how you could use data to understand it better. The journey into machine learning is one of the most rewarding scientific adventures you can take. Now, let's go out there and change the world.